You ever wonder how a massive AI model, like GPT-4 or Claude, actually reads? I mean, it doesn't see words and sentences like you and I do. To the AI, it's all just numbers. So how does it get from our messy, beautiful human language to the clean, orderly numbers it needs to work? Well, let's pull back the curtain on this secret foundational step of AI, something called tokenization. So let's start with a little puzzle. Just look at the sentence on your screen. You've got a contraction, don't. You've got an emoji. You've got a proper noun, transformers, with a question mark literally glued to it. How on earth does a machine even begin to make sense of this? What's the very first thing it does? Okay, so the simplest idea, right? Just split the whole thing up by the spaces. Seems logical, but you can already see the problems. Don't is treated as one single thing. And worse, transformers with a question mark has that question mark attached. This means the model would have to learn transformers with a question mark and transformers without one as two totally different words. That's a huge waste. So this simple approach, it's already failing. All right, let's try again. Let's get a little smarter. What if we split out the punctuation too? Now that's definitely an improvement. See? Transformers and the question mark are now separate. Awesome. But, look what happened. We've created a whole new mess. Don't is just shattered. It's now dawn, an apostrophe, and a T. The actual meaning of do not is completely getting lost in the shuffle. So what seems like it should be a really simple splitting problem is actually, just full of these tricky little edge cases. Trying to come up with a perfect set of rules to chop up any sentence you can throw at it, well, it's way, way harder than it looks. And this is the core puzzle that tokenization has to solve. And this whole thing leads us to what I like to call the Goldilocks problem. You've got methods that are too big, creating a gigantic list of words, and methods that are too small, where you lose all the meaning. What we really need is something that's, well, you guessed it, just right. Let's break that down. On one side, you have word tokenization. This is the too big approach. It treats every single unique word as its own special token. The problem? Well, for all the text on the internet, the vocabulary, that's the master list of all possible words, it becomes absolutely enormous. On the other side, you've got the too small approach, character tokenization. Just split everything into letters. The vocabulary is tiny, sure, but you lose almost all the meaning. It's like trying to read a novel by just looking at a pile of individual letters. And when I say enormous, I am not kidding. Just look at this number. The Transformer XL model, which used a pretty basic word-based method, had a vocabulary of over 250,000 unique tokens. A model has to learn a unique meaning, an embedding, for every single one of those. That's just a crazy amount of computational power. And this quote right here, it just nails the other side of the problem. What does it mean? Well, think about it. How would you even begin to teach a computer the meaning of the letter T all by itself? It's almost meaningless without other letters around it. But the word today, that has a solid standalone meaning. The too small approach, character tokenization, it just throws away way too much valuable information. So, if words are too big and characters are too small, what's the answer? Where is our just right solution? This brings us to the really elegant idea that powers pretty much all modern AI, subword tokenization. Here's the big idea. Subword tokenization is basically a hybrid. It's the best of both worlds. It keeps super common words like the or and or have as single whole units. But then it takes rare or complex words and intelligently breaks them down into smaller, meaningful chunks. We call these subwords. This is just a brilliant example of how it works. The word annoyingly might not show up very often in the training data, but I guarantee you the model has seen the word annoying and the suffix ly thousands upon thousands of times. By splitting the rare word into common parts, the model can figure out the meaning from pieces it already knows. It can understand a word it's literally never seen before. How cool is that? Let's look at a real-world case. If you feed the famous BERT model the sentence, I have a new GPU, it's easygoing at first. It's got tokens for I, have, new. But let's pretend GPU isn't in its main vocabulary. No problem at all. It just splits it into subwords it does know, GP and U. But hang on, what's with those two hash marks in front of the U? That double hash thing is basically a special little flag. It's a signal that says, hey, this part, the U, should be stitched back onto the previous token, GP, with no space in between.
It's how the model knows that GP and hash U aren't two separate things, but that they combine to make the single word GPU. It's a really clever trick to make sure the original word doesn't get lost.
So all of this seems incredibly smart, right? But it's not magic. It's not like a person sat down and wrote out all these rules by hand. These tokenizers actually have to be trained on massive amounts of text. So how do they learn the best way to chop up an entire language? One of the most famous methods is called byte pair encoding, or BPE. The way it works is actually pretty simple. It starts with a vocabulary of every single individual character. Then it scans the text and finds the most common pair of tokens right next to each other, let's say T and H, and it merges them into a brand new single token, TH. Then it just does it again, and again, and again, each time merging the most frequent pair, slowly building up a vocabulary of common subwords until it hits a size limit we set for it. Now, BPE isn't the only game in town. There are other cool algorithms out there. WordPiece, which BERT uses, is a little different. It merges pairs based on which merge would make the training data most probable or likely. And then you've got Unigram, which kind of flips the script. It starts with a huge vocabulary and then smartly throws out the least useful tokens until it's down to the right size. They all have a slightly different statistical flavor for finding those perfect subwords. And on top of all that, there's a really brilliant innovation called sentence piece. The big idea here is to stop treating the space as some magical separator. Instead, it just treats the space like any other character, even represents it with this special underscore-like symbol. And this is a total game changer because it means the same model can tokenize languages that don't use spaces like Chinese or Japanese without any special custom rules. It's incredibly versatile. Okay, we've been way down in the technical weeds. Let's zoom back out for a second and ask the big question. Why does any of this matter so much? Why is this one kind of obscure technical step so important for how AI works? Well, when you get right down to it, subword tokenization gives a model actual superpowers. It means it can handle basically any word you throw at it, even if it's brand new, just by breaking it down. It keeps the vocabulary size totally manageable, which saves a ton of memory and computing power. And most importantly, it hits that perfect Goldilocks balance. It keeps the meaning of our words while still being super efficient. It really is the foundation that all of our modern, amazing language models are built on. And so that kind of leaves us with one final big thought. We figured out this incredibly clever system for translating our language into a form machines can work with. It's all about breaking things down into known parts. But here's the question. Is breaking something down the same thing as truly understanding it? As these systems get better and better at reading our words, the next giant hurdle is moving from just processing language to actually grasping its meaning. So what do you think that next step even looks like?